In the eerie stillness of the night sky, a silent threat loomed closer than anyone realized, an asteroid with the potential to wipe out life as we know it, narrowly missing Earth in 2029. Just a few years from now, this celestial giant was on a collision course so precise that it kept scientists and astronomers holding their breath. The universe is not just a vast playground of stars and planets. It's also a fragile balance sheet where one miscalculation could spell catastrophe. Today, we dive into the story of that near miss, exploring what it revealed about our vulnerability in the cosmos, and why understanding these cosmic threats isn't just about curiosity, but about our survival. Buckle up, because what we almost face shows just how slender our safety net truly is. The first sighting, an anomalous skyward glimpse. During a typical evening, as the sky dimmed and stars began to shimmer overhead, an unusual flicker caught the eye of a seasoned astronomer stationed at a remote observatory. What initially seemed like a common asteroid streaking across the cosmos suddenly revealed itself as an anomaly, a bright, fast-moving object unlike anything cataloged in the existing sky surveys. It was a fleeting glimpse, barely a second, yet enough to leave an afterimage burned into the observer's mind. This moment would spark a series of reactions that rippled through the scientific community. The initial sighting appeared as a luminous flash against the deep black. Its trajectory was erratic, not conforming to previous asteroid paths. It darted swiftly, hinting at a small but high-velocity object that seemed to defy normal orbital patterns. The observer quickly recorded the data, noting the object's brightness, speed, and position relative to known celestial bodies. These details, seemingly innocuous at first, would become vital for analysis as subsequent observations confirmed that this was no ordinary asteroid. Instead, it was an unexpected anomaly, a potential harbinger of a celestial visitor capable of altering the course of history if it had a collision in Earth's direction. Scientists worldwide were suddenly engaged in a race against time. The object's initial trajectory suggested that it would pass close enough to Earth's orbit to warrant concern. Images and radar data confirmed the object's presence. Yet what truly set it apart was the ambiguity surrounding its origin and path. It had an unusual chemical signature, an anomaly in its spectral composition that didn't match typical asteroids or space debris. When combined with its unexpected movement, these clues hinted at an object with a potentially different origin, possibly an interstellar visitor or a fragment of a larger cosmic event. The incident underscored humanity's fragile position in the vast, unpredictable universe, a reminder of how easily an unnoticed visitor could become a catastrophe. As the days progressed, the mystery deepened. The skyward glimpse had been brief but profound, igniting debates among experts about what lines of data should be trusted and what the object's behavior signified. It essentially marked the beginning of a new chapter in planetary defense, a chapter that revealed our vulnerability and resilience. Every second of that initial sighting radiated with the suspense that such an encounter could escalate at any moment. Humanity's tiny, fragile bubble in an immense cosmos suddenly felt all the more delicate, hanging precariously in the balance, while scientists worked tirelessly to understand whether this anomaly was just a fleeting glimpse or the harbinger of impending doom. Uncovering the object, a mysterious space rock. In the vast darkness of space, an object dark and rocky drifted silently towards our planetary neighborhood. For years, astronomers kept an eye on this particular space rock, cataloging its size, trajectory, and speed. It was classified as a near-Earth object, a term that sounds benign but holds significant implications. Its diameter was estimated to be roughly 300 meters, small enough to burn up in the atmosphere if it entered at high velocity, but large enough to cause regional devastation if it struck land. Initial observations suggested that its orbit was somewhat erratic, influenced by gravitational tugs from other celestial bodies, making precise calculations complex. Over time, telescopes around the world focused on this mysterious object, trying to calculate its future path with increasing accuracy. What was particularly alarming was how narrowly this asteroid's orbit was aligned to potentially intersect with Earth's. For a brief window, the calculations swung between safe passage and catastrophe. During this period, computer models revealed a small but significant chance of impact, enough to trigger global concern. This object, often called by spacecraft experts and astronomers as a potentially hazardous asteroid, became a case study in the fragile balance between cosmic serenity and chaos. Despite the vastness of space, such objects remind humanity that we are tethered to a universe where catastrophe can strike in a blink, even when it is only the result of an unknown or poorly understood celestial trajectory. Advance warning times were deceptively short. A few detailed scans and refinements in tracking data narrowed the potential impact zone, but the true nature of the asteroid's path remained murky. Astronomers zoomed in on this strange visitor, using radar imaging to better understand its shape and composition. What they found was surprising: an irregularly shaped, rugged surface resembling an ancient, shattered relic of the early solar system. It was rich in metals and silicate minerals, and its irregular shape suggested it had experienced collisions and breakups long before entering our neighborhood. This revealed not only the threat it posed, but also provided clues about the cosmic debris that has been orbiting the Sun since its formation. As the countdown to potential impact ticked closer, humanity grappled with its own vulnerability. The object itself was a tiny ambassador of the vast dangers lurking in uncharted regions of space. While efforts centered on tracking and potential deflection strategies, the event underscored an uncomfortable truth: our planet's safety is perpetually on the brink of cosmic randomness. In the end, the object's true nature was unveiled not just as a piece of space debris, but as a stark reminder of how thin the line is between the serenity of life on Earth and the chaos of the universe beyond. Tracking the trajectory, calculations, and uncertainties. The process of tracking an asteroid's trajectory begins with gathering as much data as possible from telescopes around the world. Observatories record the object's position against distant stars over multiple nights, which allows astronomers to build a preliminary orbit. This is no trivial task. Tiny measurement errors can cascade into significant uncertainties over time, especially with objects approaching Earth from a distance that makes precise tracking inherently challenging. The initial calculations often rely on methods like least squares fitting, where data points are used to derive the best possible orbit. Yet, even the most refined models have limitations, primarily stemming from the quality and quantity of available observations. As orbit calculations progress, scientists generate what's called a confidence ellipse, representing the range of possible future positions of the asteroid. These ellipses can be surprisingly large in the early stages, encompassing a broad swath of space. The uncertainties, due to factors like atmospheric distortion, equipment calibration, and limited observation windows, introduce a margin of error that grows over time if no additional data is gathered. This is why repeated observations are vital. Each new measurement helps narrow down the trajectory, reducing the size of the uncertainty region. Until a solid trajectory is established, predictions remain probabilistic rather than certainties. The complexities multiply when calculating potential impact probabilities. Minor deviations in initial data can shift the predicted path enough to either rule out or confirm a possible collision course. For example, for the asteroid that garnered attention in 2029, initial data suggested a near miss, but small uncertainties kept the possibility alive for several years. More recent observations helped tighten the orbit, but even then, some tiny margin of error persisted, underscoring how fragile our predictive models are. As the object drew closer in its supposed approach, scientists used more sophisticated techniques, like radar ranging, which drastically improved positional accuracy but still couldn't eliminate all uncertainties entirely. Ultimately, the uncanny truth about asteroid tracking is how delicate the balance is between certainty and unknowns. These celestial bodies are tiny on a cosmic scale, but can have earth-shattering consequences. Our ability to accurately plot their courses depends on cutting-edge technology, international cooperation, and persistent observation. Yet, even then, we remain vulnerable to the whims of celestial dynamics. The near miss of 2029 was a stark reminder that while humanity has made strides in tracking space rocks, a tiny shift in a trajectory calculation could mean the difference between chaos and calm. It's a sobering testament to how fragile our grasp on the universe really is and just how much work still needs to be done to safeguard our tiny blue planet. Early warnings, the International Alert System. A network of telescopes and monitoring stations around the globe constantly scans the night sky, vigilantly tracking near-Earth objects, ENEOs, that could one day threaten our planet. This international alert system, a marvel of collaborative science, relies on early detection to buy humanity precious time, potentially decades, to prepare or deflect incoming space rocks. It's an intricate web involving agencies from NASA to ESA, JAXA, and observatories in Australia, South Africa, Chile, and beyond. Every night, data flows in from these observatories, processed through sophisticated algorithms designed to identify not just visible asteroids, but also those hidden behind cosmic noise or small enough to escape casual detection. When the asteroid that nearly collided with Earth in 2029 was first spotted, it was initially classified as a relatively small threat, until further analysis refined its trajectory. The early warning system had flagged it within weeks, prompting a cascade of scientific assessments and worldwide alerts. This is no longer a scenario of reacting after disaster. It's about anticipation. Computers crunch vast amounts of orbital data, calculating potential impact zones with alarming precision. If an asteroid's trajectory poses even a small probability of collision, global agencies mobilize to refine the orbit further, issuing alerts to governments, scientists, and space agencies. All of this hinges on the speed and accuracy of detection, because the difference between survival and catastrophe often hinges on mere days or weeks. The system's reliance on international cooperation underscores human fragility in the face of cosmic forces. A tiny asteroid's threat is not just a matter of its size, but also the speed at which it travels, sometimes tens of thousands of miles per hour. Early detection allows humanity options: deflection, evacuation, or at the very least, better preparedness. Without the alert system, a similar asteroid could strike with minimal warning, causing untold destruction. Yet, the current network isn't foolproof. Smaller or darker objects, those that don't reflect much sunlight, can slip through the cracks, lurking unknowingly until it's too late. The case of a near miss in 2029 underlines the importance of ongoing investment in these systems, because we are genuinely fragile against the vast, silent celestial vault above us. Time is of the essence. Every minute the data is processed, our chances improve. The countdown to potential disaster presses on as scientists refine trajectories and develop rescue plans. In essence, the early warning system is humanity's silent guardian, an imperfect but vital shield built on international effort, cutting-edge technology, and the understanding that in the cosmos, we remain vulnerable. We may not control the universe, but within this network, we hold a vital line of defense, standing guard against the unseen chaos of space that could one day threaten to wipe us out in a moment of cosmic indifference. The data gets clearer, refining the path of the asteroid. In the months following the initial detection of the asteroid designated 99,942 Apophis, scientists around the world pored over the incoming data to refine its trajectory. Early estimates had suggested that there was a slim but significant chance it could impact Earth during its next close approach, and the stakes fell high. As telescopes tracked its movement with increasing precision, the blurry, preliminary orbit began to clarify. Multiple observation campaigns utilized not only ground-based telescopes, but also radar facilities that could bounce signals off the asteroid, providing distance and speed data with unprecedented accuracy. This radar imaging, from facilities like NASA's Goldstone Observatory and ESA's tracking sites, allowed scientists to pinpoint the asteroid's position within a few meters, drastically narrowing down the uncertainty. The process of refining the asteroid's path highlighted how dependent our understanding truly is on the quality and quantity of observational data. Small adjustments in position, mere meters, meant the difference between a benign flyby and a potential impact scenario. During this period, advances in orbit modeling became crucial. Instead of relying on rough estimates, researchers incorporated detailed perturbations caused by Earth's gravity, the asteroid's own rotation, and even non-gravitational forces such as the Yarkovsky effect, where the asteroid's surface absorbs sunlight and re-radiates heat, subtly altering its course over time. This complexity meant that each new observation had the potential to shift predictions, sometimes significantly, a reminder of how delicate and dynamic celestial mechanics can be. This refinement process also exposed the limits of early detection systems and the importance of international collaboration. Data sharing between agencies accelerated the process. The more eyes scrutinized the asteroid, the less room there was for uncertainty. This collaborative effort transformed a vague possibility into a much clearer risk assessment. It also underscored humanity's fragility in the face of cosmic forces we can barely measure, yet can profoundly affect our existence. For a brief, tense window, the world watched as scientists darted back and forth recalculating, each update feeling like a countdown to the unknown. The pursuit of clarity in the asteroid's path was not merely about numbers, but about preparing for every eventuality, every nuance narrowing the margin of disaster or confirming safety. In essence, the tightening of the asteroid trajectory isn't just a triumph of technology. It exemplifies the ongoing struggle between human knowledge and the universe's vast, unmoving scale. As the data became more precise, it became painfully evident how delicate our grasp on cosmic navigation can be. Our planet's future, in that instant, depended on the relentless pursuit of accuracy. Every observation sharpened the focus, tightening the orbit's parameters down to a fine point, yet the uncertainty lingering in the background whispered of our vulnerability. Humanity's ability to track and understand such near-Earth objects continues to evolve, but the lesson remains clear. Even with the most advanced science, the universe's unpredictability keeps us forever on the edge of knowledge. Public reaction, panic, and panic control. When news of the asteroid's close approach spread, the initial public reaction ranged from disbelief to outright panic. The gravity of the situation became immediately apparent as headlines flashed across media outlets. Asteroid predicted to pass dangerously close, with some estimates suggesting it could cause widespread destruction if it veered off course. As social media erupted, fear intensified, with rumors and misinformation spreading faster than any official communication. Some believed the world was on the brink of disaster. Others dismissed the threat as alarmist propaganda. This divergence in response highlighted how fragile perceptions of safety can be in the digital age. Authorities quickly recognized the potential for chaos and attempted to implement panic control measures. Emergency broadcasts emphasized facts, detailing the asteroid's size, trajectory, and the updated probability of impact, aiming to ground fears in science rather than speculation. Yet, the human psyche's reaction to imminent catastrophe is unpredictable. Some people hoarded supplies, others flocked to evacuation centers, and a minority sought out conspiracy theories. The challenge for officials was to maintain calm without appearing dismissive. They had to walk a fine line, reassuring the public enough to prevent chaos, but not so much that they downplayed a genuine threat. The psychological impact of such an event can be profound. The transient nature of panic, coupled with the realization of human vulnerability, often leads to a surge in anxiety and distrust. People with pre-existing anxieties or mental health struggles could find themselves overwhelmed. Emergency management agencies deployed stress counseling hotlines and public education campaigns to reduce the fear's grip. Over time, as meteorological data confirmed that the asteroid was not on a trajectory to hit Earth, public perception shifted. The collective relief was palpable, but also served as a reminder of how thin the veneer of societal order can be when faced with potential apocalypse. Crucially, this event exposed the importance of transparent communication and the need for pre-established protocols to manage mass panic. Experiences from past crises, like the Y2K scare or minor environmental emergencies, show that misinformation can escalate fears faster than official responses. This situation underscored that, in moments of impending disaster, human beings rely heavily on trust in authorities. When that trust is broken or absent, chaos often ensues. The near miss served as a stark reminder of our fragile existence and the delicate balance public officials must maintain between alerting and calming a highly emotional audience. Government response, coordinated defense strategies. As the threat of a potentially catastrophic asteroid impact looms close to a decade ago, space agencies and governments worldwide scrambled to craft a response that could buy humanity time, and perhaps even change the outcome. At the core of this effort was the recognition that no single country could defend itself alone. A coordinated, multinational approach became the bedrock of defense strategies. The first step involved improving detection and tracking capabilities, deploying a network of telescopes and satellites globally to monitor near-Earth objects, NEOs, with unprecedented precision. These efforts revealed the importance of real-time data sharing, forcing agencies to establish communication protocols that could function seamlessly across borders, revealing a new level of international collaboration. Once a potential impactor was pinpointed, early warning systems would need to activate rapidly. This involved not only alerting national governments, but also mobilizing emergency response teams and the public in ways that minimized panic while maximizing preparedness. Drills, public education campaigns, and transparent communication became vital tools to prevent chaos. The strategic focus extended to implementing mitigation methods, including asteroid deflection techniques, such as kinetic impactors, spacecraft launched to collide with the object to alter its course, and more experimental methods like gravitational tractors or chemical disruption. Each plan required meticulous testing, simulation, and international consensus before deployment, confirming how deeply interconnected these efforts had become. On the national level, governments established specialized task forces dedicated solely to asteroid threat management. These teams coordinated with scientific institutions, military resources, and space agencies to develop layered response plans. For instance, nations with advanced space programs invested heavily in developing capabilities for asteroid redirection and evacuation strategies. A notable example involved plans to divert an asteroid shortly before impact, identifying precise launch windows for impactor spacecraft. This meant continuous refinement of trajectory calculations, understanding of asteroid composition, and consideration of unintended consequences, with every step taking into account the fragile web of human dependencies. It's a dance of precision and trust, underscoring how thin the line is between survival and catastrophe when confronting such cosmic uncertainty. Through these organized efforts, governments learned firsthand that humanity's defenses against celestial threats require not just technological innovation, but also unwavering international cooperation. We learned that in space, the smallest miscalculation can have devastating consequences, and that our collective safety depends on shared intelligence, rapid response, and persistent vigilance. The threat that once seemed distant now acts as a stark reminder. In the grand cosmic sandbox, our fragile civilization hinges on coordinated action. Every tick of the countdown emphasizes that the window to prepare is always closing, and that, in orbit's silent vastness, we are only as strong as our unity. Space agencies mobilize, defending Earth in real time. As the news spread about the asteroid hurtling Earth's way, less time than anyone hoped for remained. Astronomers had detected the object, a massive space rock approximately 1 kilometer in diameter, only a few months prior. Its path initially appeared uncertain, but gradually became clearer thanks to advancements in telescopic technology and international collaboration. What made this near-miss so chilling was the asteroid's trajectory, predicted to pass within 30 kilometers of Earth's surface, a heartbeat in cosmic terms. Frantic calculations revealed the likelihood of a direct impact, and the world was suddenly staring at the fragility of its planetary defenses. In response, space agencies worldwide snapped into action with a sense of urgency that felt almost palpable. The global community recognized that waiting wasn't an option. Countries with active space programs, NASA, ESA, Roscosmos, and others, quickly organized in a rare show of worldwide cooperation. Their initial focus was on refining the asteroid's trajectory by deploying space telescopes, radar imaging arrays, and even small satellite probes sent to track the object more precisely. Data poured in, and the countdown to potential impact shrank from years to mere weeks, amplifying the pressure on scientists and engineers to come up with a solution. This isn't merely an exercise in observation. It's a sprint to develop and deploy countermeasures. Technologies such as kinetic impactors, spaceships designed to collide with the asteroid to slightly alter its trajectory, became the primary focus of testing missions. A recent example, a spacecraft deliberately impacted a smaller asteroid to demonstrate this concept's viability. Although the asteroid approaching Earth was significantly larger, the fundamental principles of deflection remained solid, and simulation efforts exploded in complexity as they factored in variables like composition, gravity assists, and timing. The stakes couldn't have been higher. Humanity was balancing on a knife's edge, knowing that a single miscalculation could spell disaster. Adding to the tension, the tight timeline exposed the inherent vulnerability of human civilization. The mass mobilization demonstrated how fragile coexistence truly is when faced with cosmic threats. Infrastructure capable of global communication and rapid response was strained, yet this crisis showcased our collective resilience. Experts emphasize that our current capabilities still aren't foolproof. Smaller objects slipping through, or even miscalculations, could still have devastating consequences. Still, the coordinated efforts to modify the asteroid's course revealed an emerging readiness, a proof of concept that the entire human race can act decisively when pushed to the brink. The near miss left an indelible mark, a stark reminder that in the vast emptiness of space, we remain vulnerable, yet also remarkably adaptable. And perhaps that is exactly what we need to survive what's still out there. Many explosions in space, testing mitigation techniques. In the ongoing effort to defend the Earth from asteroid threats, scientists have turned their attention to the intriguing concept of using small-scale explosions in space as a strategic mitigation tool. The idea hinges on detonating miniature explosives near an approaching asteroid to subtly alter its trajectory without risking a full-scale collision. Unlike direct impactor threats, these tiny explosions are designed to create a localized disturbance, just enough to nudge a potentially hazardous asteroid onto a safer pathway, should it be detected early enough. To understand the feasibility, researchers simulate these explosions and study their impacts at a surprisingly detailed level, often utilizing space-based testing facilities and computer models. Studies indicate that these intentionally triggered space explosions would generate seismic waves and localized jets of ejecta, which could produce a fractional but meaningful change in the asteroid's velocity. The challenge lies in precisely calibrating the amount of energy released. Too much could fragment the asteroid and turn a single threat into multiple hazardous pieces, while too little may prove ineffective. Tests conducted in microgravity environments and in vacuum chambers simulate the conditions of space with remarkable accuracy, revealing the nuanced physics behind how small explosions ripple through an asteroid structure. This knowledge helps refine the timing and explosive yield needed to produce a predictable shift in trajectory, especially when the object is still at a considerable distance. The concept also emphasizes the importance of early detection. A minor explosion is only effective if it is part of a well-placed, expertly timed plan. Recognizing that asteroids are not monolithic, but often consist of loosely bound rubble piles, scientists employ small-scale explosions to test whether these structures can absorb the shock or whether they're more prone to fragmentation. Interestingly, experiments have shown that moderate detonations can, in some cases, cause a mini-explosion effect internally, loosening the asteroid's cohesion. This internal dislocation could either weaken it, making future fragmentation easier, or, if used judiciously, divert it safely. The overarching risk is humanity's inherent fragility in the cosmos. Each test, each experiment in miniature explosions underscores just how delicate our planetary safety truly is. The universe doesn't care much for our technological safeguards. What remains reassuring is that these scientific endeavors are advancing rapidly enough to give us options. While the idea of detonating modest devices in space might seem daring or even unsettling, it represents a realistic and adaptable approach in an uncertain future. As the countdown to potential collision events unfolds, every test breathes new life into the hope that, should the worst come to pass, we'll have a few more tricks up our sleeve, tiny bursts of hope in a universe full of surprises. Close Encounters, the narrow miss of 2029. In the early stages of the 21st century's ongoing efforts to monitor near-Earth objects, astronomers detected an asteroid, designated 99,942 Apophis, that sparked immediate concern. Its initial trajectory calculations suggested a striking possibility: a collision course with Earth in the year 2029. Although the asteroid measures approximately 340 meters across, even a body of this size holds the potential for catastrophic damage if it were to hit the planet. The early warnings triggered a global surge of alertness, research, and modeling, highlighting how fragile our planetary security truly is. Over months of meticulous observation, scientists refined their calculations, and it became clear that Apophis would make a close approach rather than impact, a difference measured in cosmic certainty rather than margin. As the countdown to 2029 drew closer, astronomers kept a close eye on the asteroid's path, using powerful telescopes from around the world to track minute deviations in its orbit. What they found was alarming yet fascinating. Apophis was predicted to pass within a mere 0 to 31 astronomical units, about 31 kilometers of Earth's surface. That's roughly 1/10 the distance between Earth and the Moon. For context, that's an eye-blink distance in planetary terms. It's enough to make us realize just how thin the veil of safety we often take for granted truly is. Small gravitational nudges from Earth, as well as other celestial factors, could alter its orbit slightly, but significantly, underscoring humanity's delicate dance with cosmic hazards. This near miss underscores our vulnerability, not just in terms of celestial mechanics, but also in how reliant we are on technological systems and international cooperation to identify and respond to threats. Imagine being in the dark until the last moment, an asteroid hurtling through space on a collision course, until detection is possible only days or hours beforehand. The fact that we managed to anticipate and prepare for Apophis's closest approach allowed for a global moment of unity and introspection. Yet, it revealed how little margin for error exists beyond the mere knowledge of such objects. Our planet's proximity to potentially devastating impacts isn't an abstract threat. It's a real, measurable risk that humanity continues to track with a mixture of awe and vulnerability. As the asteroid's path was pinpointed, experts emphasized the importance of ongoing planetary defense research. Strategies ranged from deflecting objects with kinetic impacts to deploying space-based laser systems capable of subtly nudging an asteroid off course over time. But the stark reality remains: for all our technological advancements, we remain fundamentally fragile, dependent on precise calculations and luck. The 2029 near-miss wasn't just a lesson in astronomy. It was a sobering reminder that the universe doesn't owe us safety. It's a stark illustration that, in the vast emptiness of space, a tiny miscalculation could change everything in moments. Humanity's persistence in observing and preparing is vital because, in the end, The difference between near miss and catastrophe often hinges on those careful, calculated seconds. Aftermath: assessing the damage and lessons learned. The near miss with that asteroid in 2029 served as a stark wake-up call about the fragility of human civilization. When scientists first calculated its trajectory, the numbers suggested a close shave, a cosmic bubble about 30 meters wide hurtling through space, yet incredible in its speed and potential devastation. If it had hit, the energy released would have been comparable to thousands of nuclear bombs, capable of leveling a city and sending shockwaves across continents. Though it ultimately passed us by, the event revealed just how small our planetary defenses are in the vastness of space, and how quickly catastrophe could strike if the trajectory slightly shifted. The aftermath forced governments, scientists, and disaster preparedness agencies to re-examine their strategies, knowing that humanity's safety might hinge on just a handful of asteroid tracking projects and rapid response plans. Assessing the damage after such an event, whether it had struck or narrowly missed, reveals important lessons about human vulnerability. For one, the importance of early detection systems became painfully clear. Despite years of advancements, several lesser-known asteroids remain undetected until they're within dangerous proximity, leaving little time for evacuation or deflection efforts. The near miss underscored that even a seemingly insignificant object could cause widespread casualties if it timed its arrival with vulnerable population centers. It also highlighted the need for better international cooperation, as space threats do not respect borders. Post-event analyses have pushed for the creation of more robust global networks capable of tracking objects hundreds of meters in size, with an emphasis on rapid information sharing. The event's lessons extend beyond technical considerations. They spotlight humanity's own sense of security. Our lives are intertwined with a fragile, thin layer of atmosphere and a relatively small planet that, despite its beauty and resilience, is subject to cosmic forces well beyond our control. The psychological impact of narrowly avoiding disaster reinforced our collective awareness of global interconnectedness and vulnerability. It sparked debates about our preparedness and whether current investments in planetary defense are enough. Building defenses, either through asteroid deflection technologies, evacuation plans, or inclusive international protocols, became urgent priorities. The event exposed gaps, but also motivated innovations, from kinetic impactors to gravitational tractors, aiming to shift incoming objects before catastrophe becomes unavoidable. Overall, what the asteroid almost hitting us taught is a simple yet profound truth. Our survival depends on the vigilance and cooperation we cultivate today. The cosmic clock clicks on relentlessly, and the universe doesn't pause to wait for human complacency. In the quiet moments after the close call, nations started to invest more seriously in space situational awareness, pushing for advancements in telescopic technology and planetary defense initiatives. As one asteroid narrowly missed snuffing out life as we know it, the collective response proved that resilience is built not just through technology, but through a shared understanding of interconnected vulnerability. Humanity's blip in the grand cosmic scale remains a fragile, precious moment, one that must inspire continuous vigilance and humility. Exploring future threats, planetary defense preparedness. In the vastness of space, objects hurtle through the cosmos at unpredictable speeds, some destined for collision with Earth. Recently, scientists identified an asteroid, often dubbed the potential threat, that was projected to pass within a close proximity in 2029. Though initial calculations indicated a slim chance of impact, further observations revealed the importance of understanding the mechanics behind planetary defense. With an estimated size of several hundred meters, this celestial body could have caused regional devastation had it struck the planet. As the countdown to its closest approach drew nearer, the world's focus sharpened on humanity's preparedness for such cosmic surprises. This near miss exposed the fragile veneer of complacency that might cover our planetary defenses. It underscored that, While we possess tracking systems capable of detecting many sizable near-Earth objects, in EOs, our ability to act decisively remains limited. Current technologies include telescopes like Pan-STARRS and space-based infrared observatories designed to monitor potential threats early on. Still, identifying an object years or decades in advance is only part of the battle. Devising effective methods to divert or destroy it is an entirely different challenge. For instance, NASA's DART Double Asteroid Redirection Test mission exemplifies proactive efforts, where a spacecraft deliberately crashes into an asteroid to alter its trajectory, an experimental step toward defending Earth, but still nascent. The approaching asteroid in 2029 was a stark reminder of humanity's vulnerability. Its projected close shave, merely a few thousand kilometers from our planet, highlighted that even objects not on a collision course are capable of exerting gravitational influences, potentially shifting tiny but significant course corrections. This threat landscape is not hypothetical. It encompasses countless small bodies whose orbits are poorly mapped or understood. The scale of potential damage ranges from localized destruction to global climate disruption, depending on size, composition, and impact site. As our knowledge advances, so does the recognition that we are playing cosmic roulette with a very thin margin of safety. Strengthening our detection capabilities, investing in deflection technologies, and establishing international coordination are no longer optional. They are imperative. Balancing the urgency of the threat with limited resources remains a conundrum. Developing comprehensive planetary defense strategies requires international collaboration, long-term funding, and a willingness to confront the reality that in space, all that stands between us and disaster can be just a matter of time or an unintended gravitational shift. The close encounter of 2029 was a wake-up call, emphasizing that the universe is indifferent to human presence. Yet it also demonstrated that with foresight and innovation, we can bolster our defenses. Humanity's silence in these moments of cosmic vulnerability could prove costly or, if we act boldly, might see us prepared for many more close calls, keeping our fragile civilization safe amid the silent threats lurking in the darkness. The science behind near misses, what we still don't know. In the vastness of space, objects on an almost incomprehensible scale zip through the void with relentless momentum, often unnoticed until they veer perilously close to Earth. The asteroid that narrowly missed colliding with our planet in 2029 exemplifies the inherent unpredictability of near-Earth objects, NEOs. Despite decades of scientific advancements and the development of monitoring systems, there remains a significant gap between our detection capabilities and the reality of these celestial threats. Our understanding of the behavior of asteroids, especially those on highly eccentric orbits, is still evolving. Variables such as the asteroid's composition, rotational dynamics, and surface properties directly influence its trajectory over time, yet many of these factors are still poorly constrained. The primary challenge lies in predicting the precise path of an asteroid years, or even decades, before a potential impact. While radar astronomy and telescopic surveys have significantly improved, there are still limitations related to size, distance, and observational windows. For instance, small differences in a spacecraft's orbit when launched or minor effects from thermal forces, like the Yarkovsky effect, where an asteroid's surface heats unevenly, can result in substantial deviations in an asteroid's predicted course over time. These tiny nudges, often invisible in initial observations, can accumulate and shift an asteroid's trajectory enough to turn a near miss into a potential impact years later. Our models still struggle to accurately simulate how Earth's gravitational influence might interact with passing asteroids over long periods. Gravitational perturbations from other planets or the asteroid's own irregular shape complicate precise calculations. There are also gaps in our understanding of how asteroids' surfaces evolve. How loose regolith and exposed rock respond to space weathering, for example, influence thermal properties and, consequently, orbital shifts. Researchers continually refine their models, but these uncertainties mean that some asteroids deemed safe today might pose a threat in decades or even centuries, as small errors cascade into major miscalculations. This uncertainty underscores humanity's fragile position in the cosmic ballet. While technology has advanced tremendously, it remains a race against the clock. Nations and scientists striving to improve early warning systems, track more objects, and develop strategies for deflecting or destroying threatening bodies. Yet, the fundamental gaps in our knowledge serve as a reminder that space remains a largely unpredictable frontier. Every near miss teaches us just how delicate our existence is, suspended in a universe where chaos and chance often hinge on the tiniest of variables. Public awareness and preparedness, building resilience. As the countdown to the asteroid's closest approach continues, less than a decade away, the urgency of public awareness and preparedness becomes impossible to ignore. Scientific predictions indicate that this celestial body, measuring approximately 340 meters in diameter, has a non-zero chance of intersecting Earth's path. While the odds remain low, the potential consequences of even a minor collision could be catastrophic, wiping out entire regions or causing widespread climate disruption. Humanity's ability to respond hinges on awareness. If people are uninformed or underestimate the threat, response times shrink, leaving little room for effective action. In recent years, governments and space agencies have ramped up efforts to educate the public about asteroid risks, illustrating the importance of widespread knowledge. Campaigns now focus less on fear-mongering and more on fostering a rational understanding of the science behind near-Earth objects, NEOs. Public drills, information dissemination via social media, and community seminars aim to build a culture of resilience, an understanding that awareness isn't just about knowing the threat, but about preparing to face it. When millions are informed about what signs to watch for and how civil agencies might respond, the collective response can be more organized, reducing panic and chaos should the worst occur. Preparing for an asteroid impact isn't solely about scientific readiness. It involves societal and infrastructural resilience as well. Cities are now incorporating asteroid impact scenarios into disaster planning, much like earthquake or hurricane preparedness. For example, some urban areas have designated evacuation routes, stockpile emergency supplies, and develop early warning systems that can deliver crucial information within minutes, sometimes seconds, of detection. Moreover, advances in asteroid deflection technology, such as kinetic impactors or laser ablation, mean that a coordinated international effort could potentially shift or destroy a threatening body before it hits. However, these technological solutions depend heavily on public and political will, which can only be sustained if awareness remains high and preparedness is embedded into everyday life. The fragility of human civilization is revealed starkly by the potential for sudden, global-scale disruptions. Unlike other natural disasters, an asteroid impact is an event that could be both unpredictable and unstoppable without preemptive action. The key lies in continuous education and investment, ensuring that complexity doesn't breed complacency. This means integrating asteroid risk awareness into school curricula, fostering volunteer networks trained in emergency response, and encouraging a mindset that recognizes resilience as a shared, collective pursuit. The closer the asteroid draws, the more urgent the message. Humanity's survival depends not just on science and technology, but on the preparedness and resilience cultivated across communities worldwide. Every individual awareness campaign, every community drill, and every technological innovation acts as a safeguard, transforming humanity's vulnerability into a network of calculated defenses. Behind closed doors, secret missions, and disclosures. In the shadowy corridors of space agencies and military command centers, classified plans for asteroid threats have long simmered beneath layers of secrecy. The asteroid approaching Earth in 2029, known to scientists as Apophis, was initially deemed a significant risk, but also sparked a wave of covert investigations and hush-hush missions. Even as public confusion and media buzz reached fever pitch, top-level discussions centered on silent contingency plans designed to mitigate what might be the greatest existential threat humanity has ever faced. Hidden behind closed doors are attempts to develop advanced deflection technologies that haven't been publicly disclosed, massive asteroid redirect mission blueprints, untested in the open, quietly shuttled through secret corridors of the world's space agencies. These projects include nuclear detonation strategies, laser-based asteroid vaporization, and gravity tractors, massive spacecraft that could slowly nudge a celestial body off its collision course. The public may learn about such efforts only after they are deemed reliable and tested. But in the meantime, a handful of scientists and military officials are reportedly working diligently on these covert solutions, often under tight security to prevent any leaks. Further entangling the web of secrecy are disclosures related to preemptive strikes, what some call Cold War-style planning, focused on the possibility that the asteroid might be too large or resilient for conventional measures. According to unconfirmed reports, several nations have discussed deploying unannounced anti-asteroid defenses, possibly involving experimental weapons tested in remote regions. These missions may involve rapid response teams, computer simulations, and unpublicized satellite systems capable of detecting subtle gravitational influences on the asteroid, hinting at a layered approach that humanity's broader gaze has yet fully comprehended. Time is swiftly ticking away, and the stakes couldn't be higher. The margin of error narrows with each passing day, and the questions about secret initiatives grow louder. What is the truth behind these covert efforts? Are we really prepared if Apophis or another similarly dangerous asteroid takes an unexpected turn? Humanity's fragility becomes painfully clear as governments and agencies remain cautious about revealing too much, perhaps fearing public panic or giving away too much technical information to unknown adversaries. The clock is relentless, and behind the shadows, a quiet battle for survival persists, one that hinges on secrets kept in the vaults of unseen missions and undisclosed disclosures, waiting for the moment they might be called into action. As the countdown approaches, it's startling to realize just how fragile our existence truly is. The asteroid, narrowly missing us in 2029, reminds us of the thin margin that separates life from sudden catastrophe. Our planet's safety depended on a combination of early detection, international collaboration, and a bit of luck, elements we must continue to strengthen. This close call underscores the importance of staying vigilant and investing in space monitoring technology, because the universe is full of surprises, some more dangerous than others. It's easy to feel small in the face of such cosmic scale, but it's also a reminder of our collective responsibility to protect what we have. If you found this eye-opening, make sure to stay tuned for more deep dives into cosmic mysteries and human resilience. Together, we're learning, adapting, and preparing for whatever the universe throws our way. Until then, keep looking up. Who knows what the stars will reveal next?